In this video, I want to explain really the intuition and give a proof behind the Rank-Nullity Theorem for finite dimensional vector spaces, which states that if you have vector spaces V and W that are finite dimensional and a linear transformation from V to W, then the rank of T plus the nullity of T is equal to the dimension of Hey, I'm Prof. Omar. Welcome to today's video. And today I really want to hone in and understand this theorem that relates the dimension of vector spaces to the rank and the nullity of a linear transformation between them. Now you notice I left this blank. The rank of T plus the nullity of T is the dimension of something. And the reason is we don't know yet if it's the dimension of V or W, but I want to get an intuition for what's going on in a picture so we can actually figure out what it ought to be. So here's a picture of what's going on. We have a linear transformation that's mapping V to W. So T is taking things from here to here. Okay, so what I want to do is analyze these pieces, the nullity and the rank, and see if we can come up with a reasonable explanation of what the relationship between things should be before we go ahead and prove things. And then we can use that to get an intuition for what the proof ought to be, so we actually understand what the proof is about. Okay, so let's start with the following. I'm going to assume that the dimension of V is n. Just quantify that for a second, and we'll make the dimension of W equal to m. So I want to pick vectors here, a bunch of them, say up to k of them. I don't know how many, that are going to form a basis for the null space, right? The null space is the set of vectors in V that get mapped to the zero vector over here. I'm going to put the zero vector right on the periphery. So what I'm saying is I'm going to take a basis for that subspace of V, the set of things that get sent to zero. And that basis is going to be V1 through Vk. So all of these under T are getting sent to the zero vector. Okay, now we have a basis for a subspace of V, and so what we can do is extend that basis to a full basis for V itself. So let's actually go ahead and do that. Okay, to extend the basis, we're going to have a vector Vk plus 1, Vk plus 2, all the way to Vn, because it's an n-dimensional vector space. And these are getting mapped somewhere, we don't know where. All right, so if we look at the image of all of our points in the full basis for V, we have a bunch of them, the red ones, going to 0, and then we have here T of Vk plus 1, T of Vk plus 2, all the way up to T of Vn. All right, so let's analyze the range of T for a second. The range of T is a subspace of W, right? And its dimension is this rank of T. So according to the variables that we have right now, the nullity of T, which is the dimension of the null space of T, is K. We've made it that way because we've picked random K vectors to be the basis for the null space. And now we want to analyze what's happening with the rank of T. Okay, so here are some vectors in the range of T. And then we also have T of V1, T of V2, all the way through T of Vk, but these all get sent to 0, so they really don't contribute anything. Now if we think about what T of any random vector is, the image of any random vector in this vector space is going to be T of V. But T of V, because V is a linear combination of the VI's, T of V is going to be a linear combination of the T of the VI's. So this is going to look something like T of V1 times some scalar C1 up to T Vk times some scalar Ck. And then we have all of these other values up to Cn t of Vn. Right, we get this because V is written as C1 V1 plus C2 V2 up to Cn Vn, and we use linearity of the linear transformation T to express things like this. Now all of these vectors here are going to 0. So T of V really can be expressed as a linear combination of the part of the basis of V that runs from the vectors Vk plus 1 up to Vn. So another way to think about this is every single vector in V, its image under T can be written as a linear combination of T of Vk plus 1 up to T of Vn. This is an arbitrary vector that we chose, so this means that the range of T, everything that T sends V2, okay, so that actually means that the range of T is the span of these vectors. So the range of T is the span of T of Vk plus 1 up to T of Vn. So maybe it's the case that these vectors actually aren't just a spanning set, but form a basis. Now, if they did, the number of vectors in here is, we start with k plus 1 up to n. N is k plus n minus k. So the number of vectors here is n minus k in total. That would make this thing n minus k, which would make the sum of the dimensions n, and that's the dimension of V. So it seems like this is the dimension of V here, if these vectors form a basis for the range. Now, the only way they would form a basis for the range is if they were actually linearly independent. Now, what would give us an intuition of whether or not that's the case? So the idea is if there was some combination of these vectors that was sent to 0, then we would have this expression for some scalars ck plus 1 through ck being sent to 0. Okay, but that would mean that if we pulled in the scalars, the corresponding vector v, which is ck plus 1, vk plus 1, all the way to cn vn, would be sent to 0 as well. Right? Which would mean that that vector v, which I'll write explicitly now, as ck plus 1, vk plus 1, up to cn vn, would be something that lies inside of the null space of this linear transformation. Which would mean that this vector, because we've picked these vectors to be a basis for the null space, would mean this vector is a linear combination of these ones. But there's a problem with that, because if this vector is a linear combination of these ones, we can express this as, say, like a, or maybe c1 v1 up to cn vn. Then moving things over, we would have 0 being a linear combination of all these vectors, which is impossible because this thing here is a basis for v. We can't have a non-trivial linear combination of these vectors equaling the 0 vector. So this indeed actually serves as a basis for the range of T, which means that we have this relationship between the rank and the nullity of T. But again, I want to hone in on the actual intuition behind everything here to really understand what's happening. You have a basis for V, and you've partitioned it into two pieces. You've started by taking the stuff that gets sent to the null space and then extending it to a full basis. All the stuff in the null space really doesn't contribute at all to the image of T. So the real contributors are the images of these remaining vectors here. And by contributors, what we really mean is they form the core of what the image of T is structurally based on. So any vector that is in the image of T will be a linear combination of these. And because we've gotten rid of everything that gets sent to 0, these really form a basis for the image. And the number of vectors in them is precisely n minus k. So there you have it. Sort of an intuitive picture of why the rank-nullity theorem makes sense, together with an overarching idea of the real components of the proof. But I wanted to present it in a way that sort of broke things down in terms of intertwining the intuition and then the actual mathematics that goes into the details of some of this. So I hope you liked today's video. If you did, click the like button. And if you'd like to see more videos like this, subscribe to the channel.